Today we've got a really nice finite sum of reciprocals of sine squared. And I was first turned on to this sum by a viewer who emailed me, but then searching around the internet I found a couple of posts on the Math Stack Exchange about this sum, and maybe here's a link to one of them if you'd like to check it out. We're using an evaluation technique that's fairly similar to one of the posts in this thread. Okay, so let's get started. Well, before we get started, let's look at the sum. We've got the sum as m goes from 1 to n minus 1 of 1 over sine squared pi m over n. And I should point out here that this is going to be valid as long as n is bigger than or equal to 2. And that's because, well, if n is equal to 1, we'd have the empty sum. That's a sum starting at 1 but ending at 0. Okay, so let's start by recalling the Pythagorean trig identity, which says that sine squared is equal to 1 minus cosine squared. But of course, we can factor 1 minus cosine squared as 1 minus cosine theta times 1 plus cosine theta. But note that we've got objects of the form 1 over sine squared theta. But writing that sine squared as this product of 1 minus cosine times 1 minus sine motivates us to use partial fraction decomposition. And in fact, this decomposes as 1/2 times 1 over 1 minus cosine theta plus 1 over 1 plus cosine theta. So I'll let you multiply out, or I should say find common denominators on the right hand side and put this all back together and see that this in fact does hold. So that means I can apply that up here. So our goal sum will be equivalent to the following two sums. So we've got the sum as m goes from 1 to n minus 1 of 1 over 1 minus cosine times pi m minus n. And then I'm going to write this as minus 1/2 times the sum as m goes from 1 to n minus 1 of 1 over negative 1 minus cosine pi m over n. So in other words, I just took this second portion of our partial fraction decomposition and I multiplied it by negative 1 squared and broke it up like that. Okay, great. Now, next up, I'm going to introduce a little bit of notation. So let's set x sub m equal to cosine of pi m over n. And then that allows us to write this thing as follows. We have 1/2. Then I'm going to write this as the limit as x goes to 1 of the sum as m goes from 1 to n minus 1 of 1 over x minus xm. So that limit as x goes to 1, we'll put a 1 right here. And then this cosine of pi m over n term, that's just what we set equal to xm over there. Okay, and then likewise, this next thing will be 1/2. And then the limit as x goes to negative 1 of the sum as m goes from 1 up to n minus 1 of 1 over x minus xm again. Okay, nice. But now I'm going to look at one of these sums. Well, really looking at one of them is the same as looking at both of them if we do it prior to taking the limit. And I'm going to notice that we can write these using an interesting trick. Okay, so let's first expand this out. So this is going to be 1 over x minus x1 plus 1 over x minus x2 plus dot 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 up to 1 over x minus xn minus 1, given that that's the top part of our sum. But now let's observe that assuming that all those xi's are different, which they are based off of our definition over there, a common denominator will simply be the product. And then furthermore, each of the summands in the numerator will be a product of everything except one of the terms, depending on which portion of the fraction it came from. So in other words, it's going to look like this. So we'll have x minus x2 multiplied up to x minus xn minus 1 plus x minus x1 times x minus x3 multiplied up to x minus xn minus 1 plus dot dot dot. And then, well, that's going to end at this last term right here. So I'll let you write it down a little bit more carefully if you need to. And then in the denominator, we have x minus x1 multiplied up to x minus xn minus 1. But now let's look at that numerator. And the numerator is in fact the derivative of the denominator. And that's the really important thing to notice here. So that denominator is a product. If we take the derivative by the product rule, well, one of those terms will disappear one at a time. That's because they're simply linear terms where the coefficient is 1. So I'm going to rewrite this as p prime of x over p of x. And this is going to be where p of x is equal to x minus x1 multiplied up to x minus xn minus 1. Okay, nice. But now let's observe that since none of those xm numbers are equal to 1 or negative 1, that means that this type of object right here is continuous at 1 and negative 1, meaning that taking a limit is the same thing as plugging things in. All of this is to say that we can rewrite this line as 1/2 times p prime of 1 over p of 1 minus 1/2 times p prime of negative 1 over p of negative 1. Now we just have to determine those. Okay, so let's see the trick that we'll use in order to finish this thing off. Okay, so this is where we are so far. Our goal sum is equal to half p prime of 1 over p of 1 minus half p prime of negative 1 over p of negative 1, where p of x is the product of x minus x1 times x minus x2 all the way up to x minus x sub n minus 1, where x sub m is cosine of pi times m over n. And you might say, well, where does this really help us? Well, now we're going to define a certain family of polynomials. And it's going to be like this. So we're going to define Tn of x, which, like I said, is a polynomial. It's in fact a polynomial with real coefficients. So we can say that Tn of x is in R adjoin x. And we're going to define it by the following rule. So Tn evaluated at cosine theta is equal to cosine of n times theta. Okay, nice. But now let's observe that if we take the derivative both sides of that with respect to theta, we'll get minus sine theta times Tn prime of cosine theta equals minus n times sine of n theta. So again, that's just by taking the derivative. But now let's see that Tn prime of cos theta is in fact equal to n times sine n theta over sine theta. Okay, great. And now the question is, where is that equal to 0? So let's observe that this is equal to 0 if and only if n times theta is equal to a multiple of pi. So that means it's equal to 0 plus minus pi plus minus 2 pi, so on and so forth, while theta is not a multiple of pi. So that means theta is not equal to 0, plus minus pi, plus minus 2 pi, so on and so forth. Because what we want is for the numerator to be 0, but the denominator not to be 0. Well, observe that that means that theta can take the values pi over n, 2 pi over n, all the way up to n minus 1 pi over n. And in fact, after that, it starts repeating. But really the takeaway here is that Tn prime evaluated at x sub m, that's the same thing as plugging in pi m over n into this formula, which will give us 0. So in other words, all of these x sub m's are zeros of this t sub n. But in fact, and we won't show this, is that x sub m makes up all of the zeros of the Tn prime. And also there are no repeated zeros. So what that means is that Tn prime of x is equal to some number, we can always factor a number out, times x minus x1 all the way up to x minus xn minus 1. Oh, but that's going to be equal to some number times p of x, by the way that we defined p of x right up there. But then if Tn prime is really just a multiple of p, then that tells us that p prime of x over p of x is the same thing as Tn double prime of x over Tn prime of x, because the constant term will cancel. Okay, so now let's replace these p's with Tn primes, and let's see where that takes us. Okay, so we were just able to write our goal sum in the following form with these new Tn polynomials. And I should point out here that this forms a special family of polynomials known as Chebyshev polynomials. But now we need to go through the process of figuring out Tn prime and Tn double prime evaluated at 1 and -1. Okay, so let's recall the defining property up here that Tn of cosine theta is equal to cosine of n theta. So let's take the derivative. You know, we did that before, but we'll do it one more time. And let's observe that we'll have minus sine theta times Tn prime of cosine theta is equal to minus n times sine of n theta. Okay, but that means that Tn prime of 1 is equal to, I'm going to write this as the limit as theta goes to 0 of Tn prime of cosine theta. So that's given the fact that cosine of 0 is equal to 1. But in turn, that's going to give us the limit as theta goes to 0 of, let's see, we have n times sine n theta over sine theta. But I think it's well known that sine n theta over sine theta has a limit of n. So that gives us a value of n squared for Tn of 1. Okay, well what about Tn prime of -1? Well, that's going to be the limit as theta goes to pi. That's because cosine of pi is -1. So of Tn prime of cos theta. But now that's going to be the limit as theta goes to 0 of n times sine n theta over sine theta. But now at this stage, maybe we'll use L'Hopital's rule. So applying L'Hopital's rule, we'll get the limit as theta goes to 0 of n squared times cos n theta over cos theta. And this should have been going to pi. Okay, nice. But now, like we said before, cosine of pi is -1. But then you can check that cosine of n times pi is -1 to the n. So that's going to, in the end, give us -1 to the n plus 1 times n squared. Okay, So let's make these replacements right here. So this Tn prime of 1 will be n squared, whereas this Tn prime of negative 1 will give us an n squared, and then we can say this is plus minus 1 to the n over 2, just absorbing some of those minus signs. And now we'll want to work at finding some values of Tn double prime. Okay, so now we're ready to further our calculations to find some values of Tn double prime. So let's start with this thing that we had before, which was Tn prime of cos theta equals n times sine of n theta over sine of theta. And just like we did before, we're going to take the derivative of this with respect to theta. So let's see, using the chain rule on the left-hand side will give us minus sine theta times Tn double prime of cosine theta. And then on the right-hand side, we'll need to use the quotient rule. So we'll have n squared times cosine of n theta times sine of theta. So that's by taking the derivative of the numerator. And then we'll have minus n times sine n theta times cosine of theta. That's by taking the derivative of the denominator. And then this is all over sine squared theta because we have to square the denominator. Now, next up, we'll divide by a minus sign, but then dividing by a minus sign will build this denominator to a sine cubed, and it'll switch the order of subtraction. So that gives us Tn double prime of cos theta is equal to n times sine of n theta times cos theta minus n squared times cos n theta times sine theta. And then this is going to be all over sine cubed theta. But now observe that we've got an indeterminate form on the right-hand side. If we plug in theta equals 0 to achieve Tn double prime of 1, we'll get 0 over 0. So here we'll use L'Hopital's rule. But let's just point out here that we are taking the limit as theta goes to 0. So on the left-hand side, that will achieve Tn double prime of 1. Recall that Tn are polynomials. So limits for polynomials on the one hand are really just plugging numbers in. So that's the view that we're taking on the left-hand side. And then on the right-hand side, we'll use L'Hopital's rule. So let's see, this is going to turn into the limit as theta goes to 0. The derivative of the numerator is a little bit of a chore, but everything cancels out kind of nicely to leave us with n cubed minus n times sine of n theta times sine of theta. So like I said, that's the derivative of the numerator after doing a little bit of simplification. And the derivative of the denominator using the chain rule will give us 3 sine squared theta over cosine theta. But now one of these sine thetas will cancel with the sine theta in the numerator. So let's make that happen. And then the other one, the sine n theta over sine theta, well, that limit will be equal to n. In the end, giving us a value of n to the 4th minus n squared over 3. So that's the value of our Tn double prime of 1. And then very, very similarly, but I won't do the calculation, we get Tn double prime of negative 1 is equal to minus 1 to the n times n to the 4th minus n squared over 3. Now we're ready to finish it off. Plugging these values of Tn double prime, we'll notice that this n squared will cancel with a factor of n squared in the numerator of each one. Then in the second one, a minus 1 to the n will cancel with this minus 1 to the n. And then we'll have the same thing that we're adding together. Oh, but we've got a half in front of each. So in the end, it's all going to simplify down to n squared minus 1 over 3. And there you have it. That's the final value of our sum. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.